Welcome to the second of our climate literacy webinar series. We're really excited to have you here, and we're really excited to hear from the speakers that we have ahead of us. Today we're going to be focusing on the evidence that we have of the factors that have caused the rise in global temperatures over the past century. And for those of you that are users of next-gen science standards, that should sound very familiar to you, because this is in fact one of the middle school performance expectations that you probably have looked at before. Before we go any farther, of course, I want to acknowledge that wherever you are on the land of a unique tribal nation. And as science teachers, we are really fortunate to have our guiding document be the K-12 Science Education Framework, which actually intentionally acknowledges that there are other ways of knowing, and that there's an increasing recognition that the diverse customs and orientations that members of different cultural communities can bring to both formal and informal science learning contexts. And this is something we went much more into depth on our last webinar, but always something that we should be remembering and bringing into our teaching. I also just wanted to bring in a little fun to our big opening here today. For those of you that are football fans, that wouldn't be me, but for those of you that are, in anticipation of the 50th Super Bowl, our friends at Climate Central put together this graphic, which showed the football season, which is about September to December, temperature trends in all the NFL cities for the last 50 years. And of course, not surprisingly, all of those cities have warmed over time at different degrees, of course. And you might be able to pinpoint some of the places that you have been or some of the games that you have watched to have a sense of that. I also bring this up just to highlight a particular resource, a place you might want to go if you're looking for graphics that are really easily digestible and sometimes made fun through the Climate Central website, and I'll share that later. At this point, I'm going to ask Ellen Ebert to just pop in and give a brief introduction to Climb Time.
Hi, thanks, Kristen. Thanks so much. Hi, everyone. My name's Ellen Ebert. I'm the Director for Science and Environmental and Sustainability Education at the Office of the Superintendent of Public Instruction here in cold Olympia, Washington. I'd like to make a couple of thank yous before we get started today. First of all, we need to thank our Washington State Legislature for providing the one-year funding that we have for the Climate Science Initiative, which we have affectionately named Climb Time. I'd like to thank my Washington team of Amber McCulloch, Science Specialist here at OSPI, and Dr. Philip Bell and Dr. Deb Morrison at the University of Washington's College of Education. A big thank you to all the people behind the scenes at OSPI for their support and professionalism. A huge thank you to our 16 projects and their respective teams that are doing the Climate Science and Science Education Initiative work across the state. Warm thank you to Kristen Poppleton of Climate Generation and Frank Neapold of NOAA for their generosity of time, critical thinking, and collaborative friendship throughout the initiative process. And last but not least, a big thank you to our guest speakers for their time today. It's a very, very generous gift of their time with us. Thank you to Dr. Ben Santer and Jenna Totz. So back to you now.
Just an acknowledgement briefly, of course, of our supporting partners beyond Ellen just said. NOAA, Climate Office, you'll hear from Frank Neapold a little bit later, the Clean Network, and Climate Generation, where I work as Director of Programs, and our guest, Jenna Totz, is the Climate Change Education Manager, and you'll hear from her later as well. So at this point, it is my distinct privilege of introducing our guest speaker today, Dr. Ben Santer. Ben is an atmospheric scientist at Lawrence Livermore National Laboratory. He studies natural and human fingerprints in observed climate records. His early research contributed to the historic 1995 conclusion of the Intergovernmental Panel on Climate Change, The balance of evidence suggests a discernible human influence on global climate. And those words are extremely important. If you have been following climate change research over time, you know this. He served as lead author of a key chapter of that report. Since '95, Ben has identified human fingerprints in atmospheric temperature and water vapor, ocean heat content, sea surface temperature in hurricane formation regions, and many other climate variables. He holds a doctorate in climatology from the University of East Anglia, England. After completing his PhD in 1987, he spent 5 years at the Max Planck Institute for Meteorology in Germany, where he worked on developing and applying climate fingerprint methods. Ben joined Lawrence Livermore Lab in 1992. He's received a number of awards for his research, which include a MacArthur Fellowship in '98 and a membership to the U.S. National Academy of Sciences in 2011. The most significant awards are the friendships he has made during his career. In addition to his research, he cares deeply about the communication of climate science to a wide range of audiences. He writes for the Scientific American blog, which you should really check out. I'll have a link to all those articles. They're really, really lovely articles. And has appeared on Late Night with Seth Meyers, which you should Google. Together with Chip Duncan and Dr. Hernando Garcon, Ben is a member of the 3 tenors of climate change. The tenors are devoted to the task of improving public understanding of the science and impacts of human-caused change. In his spare time, Ben is an avid rock climber and mountaineer, and we at Climate Generation are proud to have him as one of our advisory board members. I don't know if Ben is happy I shared this, but I found this when I was looking for his photo, and I just love it. It's great, and another highlight of another place to go for information, skepticalscience.com, where they cite Ben as one of the most important folks to really listen to and read about when it comes to climate change. So with that, Ben, I'm going to stop sharing my screen and give you the opportunity to share yours.
Thank you very much for that kind introduction, Kristen. Let me bring up the presentation here.
Perfect.
It'll just take a few seconds to bring this up since it's rather a big file. And here we go. Does that look okay to everyone?
Perfect.
Well, thank you very much for giving me this opportunity to speak to you. And as Kristen mentioned, after the IPCC second assessment report in 1995, I learned from that experience that part of my job was not only to do the science and improve our understanding of the nature and causes of climate change, but also to talk to people, hopefully in plain English, about what that scientific understanding is. And again, as Kristen mentioned, most of my own research actually focuses on the question that has been posed and that you're trying to address. What is the scientific evidence of the different factors that change global mean temperature, and what are the main drivers of the substantial increase in global temperature over the past century? So that's what we'll talk about today. What are we dealing with? These are estimates of changes in the average temperature of the land surface and the ocean surface from roughly the 1850s through to the present. This is from a fellow, Robert Rohde at UC Berkeley. Check out the information that he has on his website. Amazing stuff. Again, very, very easy to digest images of a number of different aspects of temperature change, both instrumental records, surface thermometer records, but also information that goes back in time, thousands or even hundreds of thousands of years, a great resource for teaching. Here from Robert Rohde is the best information we have about how the average temperature of the planet has changed. These are from different groups, a group in the UK, the Hadley Center, and the Climatic Research Unit, that's the blue line, a group at the Goddard Institute for Space Studies in New York, a NOAA group in Asheville, another UK group, C&W, Cowton and Way, and a group at the European Center for Medium Range Weather Forecasts, and then the Berkeley group itself. You can see that all of these 6 different estimates made by different groups using different ways of processing the same raw surface temperature measurements concur in showing a picture of a warming Earth. And that warming is roughly 1.1 to 1.2 degrees Celsius, so nearly 2 degrees Fahrenheit, from the mid-1800s through to the present. So what we're going to try and understand today is what are the main drivers of this overall increase in the temperature of the Earth's surface. And it's not only an increase in the temperature of the Earth's surface. These are satellite measurements that we have from 1979 through to the present of the temperature of the lower atmosphere, the troposphere. And these measurements from 3 different groups, one at the University of Maryland, one at the University of Alabama, and one here in California, show global scale warming over the last 40 years. We now have 40 years of satellite record of roughly 3/4 of a degree Celsius, 1.25 degrees Fahrenheit. And when we look at time series like the one I just showed you for the surface temperature, or this one here, you see an overall warming trend, but a lot of interesting wiggles. And part of our job as scientists is to understand those wiggles. You can see, for example, in 1982, there's a dip, and that's caused by the eruption of El Chichon in 1982. Very large volcanic eruptions can cool the planet for a year or even longer at a time. The dip in 91, 92 is due to a different eruption, the eruption of Mount Pinatubo in the Philippines. And you can also see these warm spikes, like the big spike in 1997, 98, the spike in 2015, 2016. That's the warming caused by El Nino. When you have very large El Nino events, those are purely natural fluctuations in the climate system. You can warm the planet. And we'll be talking about all of these things, the overall rise in temperature and the factors driving it, and also these natural factors like El Niños, like volcanic eruptions. So without further ado, this is basically what my talk will cover: natural effects on climate, changes in the sun, changes in volcanoes, and these internal oscillations, things like El Niños, and then the human effects on climate. By burning fossil fuels, we increase levels of heat-trapping greenhouse gases in the atmosphere. We also produce particulate pollution, things like sulfate aerosol particles, soot from various combustion processes, and we cut down forests and transform the surface of the land. So a key take-home message is all of this stuff is happening simultaneously, the natural factors and the human factors. Climate change isn't an either-or proposition, all human or all natural. It's some combination of all of these natural and human effects. And the challenge in my world is to separate them, is to try and tease out the individual effects on global temperature of each of these factors. Let's look at the sun first. So since the late 1970s, we have measurements from space of the sun's energy output. And that's what you see here. These are measurements of the amount of the sun's energy, something called total solar irradiance, that reaches the top of the atmosphere. And you can see these nice, roughly 11-year solar cycles. You can also see that over the period we've actually monitored the sun's energy output from space, there's been no overall increase. So what's going on with these 11-year cycles? The bottom line here is that they're related to changes in sunspots on the sun's surface. And we've been measuring sunspots since the 1600s. When you have a very large number of sunspots, that's called solar maximum. A small number of sunspots is solar minimum. And more sunspots mean more solar activity and more of the sun's energy arriving at the top of the atmosphere. We know, say, from Chinese records of the number of sunspots on the sun that go back, like I said, to 1600, that the sun is a variable star, and that in addition to these 11-year cycles between high sunspots and low sunspots, there are also times when sunspots disappear altogether, such as the so-called Maunder minimum, a very cold period in Earth's history. So part of the job of scientists is to try and understand the solar effect on climate. And one simple way of looking at that is looking at the last 40 years when, as I mentioned earlier, we actually have measurements from space of the sun's energy output. So you can see that during the period of time we've monitored the sun's energy output, the average temperature at Earth's surface has increased. That's the blue line in the top panel, but the sun's energy hasn't increased. So if you're arguing, as many people do, that an uptick in the sun's energy output explains all of the surface warming, that just doesn't explain the blue curve. It's a fundamental difficulty that you face if you argue that the sun explains all surface warming. Well, another difficulty is that if the sun explained all surface warming, you would expect to see heating throughout the full vertical extent of the atmosphere, from the surface right to the upper atmosphere, but we don't see that. So for many reasons, the sun as a primary driver of the blue curve of this increase in surface temperature just doesn't fit the bill. Let's look at volcanoes now. My one claim to fame in the climbing world, Kristen was kind enough to mention that I'm a rock climber and mountaineer, is that I was one of the last guys to climb Mount St. Helens before it erupted. So since 1980, which is when Mount St. Helens erupted, I've had a deep and abiding personal interest in volcanoes around the world. And this is actually a picture from April 1980, climbing Mount St. Helens by what was called the Dog's Head route. Well, how do we know about volcanic effects on climate? We can look at these beautiful ice core records, both from Antarctica, which you see on the left, and from Greenland, which you see on the right. So scientists have been drilling cores in the ice for decades now, and using that information to try and understand changes over time in things like carbon dioxide, but also in things like sulfates produced by large volcanic eruptions. So large volcanoes emit sulfur dioxide. Some of the gases that the volcanoes emit form particulates, and the winds, the atmospheric circulation, carry that volcanic material even to remote places like Greenland and Antarctica, and some of it is then deposited on the surface of the ice. And by going deeper and deeper down the core, you can go further back in Earth's climate history. This, for example, is an ice core from West Antarctica, and that black band there is the signature of a large volcanic eruption. So we can use these natural time machines, these ice cores, to go back many thousands of years. This, for example, shows you from the Greenland ice core, very large volcanic events going back 5,000 years. That's what those big spikes are. Again, it's a wonderful way of getting information about deep time changes in volcanic activity. But more recently, we can also use satellites, not just ice cores, to study changes in volcanic material in Earth's atmosphere. And that's what you see here. These are really beautiful measurements. So since the late 1970s, we have satellites that look at starlight, moonlight, and sunlight, and how the transmission of that light through the upper atmosphere is interfered with by gunk in the atmosphere. So the more gunk you have, the more the passage of light through the upper atmosphere is interfered with. And we can measure that. And for example, that blue line that you see there in about 1991 is the big change in the amount of volcanic material in the atmosphere after the eruption of Mount Pinatubo in the Philippines in June 1991. The spike in about 1982 is El Chichon in Mexico. So we have many different ways, ice cores, satellites, of studying volcanic effects on climate. This is just to show you that it's not only the big eruptions like Pinatubo that can influence the atmosphere, but even smaller eruptions. This is Tavurvur in Papua New Guinea, can get material, volcanic material, into the upper atmosphere and influence climate. And they're not only in the northern hemisphere. This is Calbuco in Argentina in 2015. So part of my job is to study these volcanic effects on climate. And the bottom line is that they're influential, the bigger ones, for 1 year, 2 years, maybe even a little longer than that. But our best understanding is that they cannot explain the warming that I showed you in the first couple of slides of my presentation. They can't explain that overall increase in the temperature of Earth's surface or the lower atmosphere, because again, volcanoes cool, and what we've observed is this strong warming signal. All right, let's move now to changes that have nothing to do with the sun or volcanoes, that are purely related to internal variability of the climate system. And I'm going to show you a quick NOAA video here, just to illustrate variability associated with El Niños and La Niñas, perhaps the dominant mode of internal variability in the climate system. So let's hope this works. It's a brief video, only about a minute and a half long or so.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Niño. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern US, and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Niña, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Niña can lead to drought in the southern US and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Niño and La Niña together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the US, but in many parts of the globe.
I really like this little video because it shows you a three-dimensional representation of El Niños and La Niñas, not just what's going on at the surface, but also what's going on below the surface, how warm water and cold water slosh around across the Pacific. Very nice teaching tool. And here, for example, is an estimate of how El Niños have behaved over the last 60 plus years. And you can see this very rich natural variability. There have been times with large El Niños, like the one I mentioned earlier, the one in 1997, 98, that on average warmed the planet, and times when there have been big La Niñas, like one in 1973 to 1974. This is one example of this kind of natural internal variability of the climate system. And there's a whole zoo of these things, not just El Niños and La Niñas, but many other different modes of internal variability in the climate system. And if you're a climate scientist, that's what you do. You study these things, you know and love them, and you try and understand their patterns and how they influence climate all around the world. So all of this was natural stuff: the sun, volcanoes, internal variability. And the next bit is human effects on climate. And the first is changes in greenhouse gases. So one false narrative out there is that our understanding of greenhouse gases and their effects on climate is something that is very, very recent. That's not true. We've been trying to understand the effects of greenhouse gases since the 1700s, and arguably even earlier than that. Fourier is generally first credited with comparing Earth's atmosphere to a greenhouse. Tyndall made some of the first measurements of how different greenhouse gases, like carbon dioxide, actually trap heat. He made those measurements under controlled conditions in labs. And Arrhenius is generally credited as the first person to try and model the impacts of human-caused increases in CO2 from burning fossil fuels on Earth's surface temperature back in the early 1900s. So our understanding of the greenhouse effect isn't something that just goes back a couple of years or a couple of decades. It's rich and it's long-standing. I wanted to show you next where scientists make measurements of greenhouse gas changes. These are largely NOAA measurements made at many locations around the world. And I'm going to mention one location here in particular, Izania, which I had the privilege of visiting just last year. So Izania is an observatory on the island of Tenerife off the African coast. These weird things that you can see here are called photometers. They actually measure the amount of aerosol, in part volcanic aerosol, in the atmosphere. And here, for example, if you look at the top left panel, are measurements made at the Izania Observatory of the amount of CO2 in the atmosphere. So since 1985, when they started making CO2 measurements at Izania, carbon dioxide in this rather remote location has increased from about 345 parts per million to nearly 410 now. So that sort of brings it home to you when you're in the middle of the ocean there, far removed from local pollution sources, and you see the stark reality of the increases not only in CO2, but also these other greenhouse gases, methane, nitrous oxide on the bottom left panel, and various chlorofluorocarbons. We are literally, through our activities, changing the chemical composition of the atmosphere. The most famous record of CO2 increases at the Mauna Loa Observatory in Hawaii. That started in the late 1950s. Charles Keeling is generally regarded as the father of these measurements at Mauna Loa. And again, they show an increase from less than 320 parts per million to over 400 parts per million now. how do we know that most of this increase in atmospheric CO2 is on us, is due to human activities, primarily the burning of fossil fuels? We know from simple bookkeeping, we know how much fossil fuels we burn in countries around the world, so we can figure out how much CO2 is emitted from that fossil fuel burning. And we also know because oxygen in the atmosphere is decreasing and because isotopes of carbon are changing. So why is the oxygen important? Oxygen is important because when you burn carbon, that requires oxygen. So the more carbon we burn, the more we should be depleting oxygen in the atmosphere. And you actually see this here at the Cape Grim Observatory in Tasmania. Again, rather remote location. We see this depletion of oxygen consistent with human-caused fossil fuel burning. As I mentioned, we know that when we burn fossil fuels, we also affect the ratios of lighter and heavier isotopes of carbon. And we can see that change in the ratios of lighter and heavier isotopes of carbon. They are a fingerprint, if you will, of human-caused fossil fuel burning. So again, when we look at the Mauna Loa record, when we look at the record I showed you from the Azania Observatory, we don't have to speculate about the causes of those CO2 increases. We really do know pretty well that the lion's share of those increases, 75 to 80%, is human-caused fossil fuel burning. We can also go further back in time and we can look at bubbles of air trapped in ice in Antarctic ice cores and Greenland ice cores. Just some eye candy here showing you what those bubbles look like. Scientists have figured out very clever ways of extracting the air trapped in those bubbles that's been isolated from the atmosphere for thousands or even hundreds of thousands of years. And you can then measure the small concentrations of greenhouse gases in those bubbles and have a natural time machine. That enables you to do something like this, to look at a record of the last 800,000 years of CO2 levels in the atmosphere, compiled from a variety of different Antarctic and Greenland ice cores. And we can see this nice, in that red curve, ice age cycle, the beat of the ice ages. And on ice age timescales, levels of CO2 vary from about 180 to about 280 parts per million. Where we are now, over 400 parts per million CO2 in the atmosphere, is uncharted territory, at least in the last 1 million years, and probably much longer than that. So the sobering reality is, based on the mix of energy we use in the 21st century and how much energy we use, we will determine where CO2 levels are by the end of this century. So that decision rests with all of us here on the planet, not just with folks in Washington, D.C. In addition to changing greenhouse gases, we've also changed particulate pollution. Particulate pollution isn't a figment of some mad scientist's imagination. This is NASA imagery on the left of the Himalayas at a certain time of year when there's a lot of burning of agricultural waste, urban construction, industrial pollution. And on the right, you can see what's called the optical depth, which gives you a measure of how much of the sunlight that the sun emits is actually reaching the Earth's surface. So in these very heavily polluted areas, there are times at which the amount of sunlight reaching the surface is reduced by about 2/3. So in regions with very high loadings in the atmosphere of particulates like this, you can affect the climate both locally and regionally. Again, we can see this stuff from space. It's not something that is reliant on computer models of the climate system in order to understand how particulate pollution affects climate. Again, we can look at ice core records. This is a very simple graph, but I kind of like it, from the Greenland ice core, GISP-2, and the black line shows an estimate of human-produced sulfate particulate pollution in that ice core, and the red line shows human-caused emissions from industrial sources of sulfate. So as industrial activity ramped up, we saw this rapid ramping up of emissions and atmospheric loadings of sulfates in Greenland ice cores. And then that decrease after about 1970 is in part due to our dawning recognition that sulfur pollution was not good, had lots of nasty consequences like acid rain. In the United States, we introduced the Clean Air Act. We tried to clean up sulfate emissions from certain sources like power plants. And that had some implications then for the amount of sulfate particulate pollution post-1970. So again, these things are not conjecture. We can see the signals of human-caused particulate pollution in ice cores from space, and it's not only greenhouse gases and particulate pollution. Human activities have transformed the surface of the land. This is satellite imagery from Paraguay, that's A, from Indonesia, that's B, from the United States, that's panel C, and from the former Soviet Union, that's panel D, of changes in forest coverage from 2000 to 2012. The red is the thing I'd like you to focus on. That's forest loss, basically where we've cut down forests. So human activities are transforming the surface of the land. And when you do these things, you affect the moisture from the Earth's surface and soil that reaches the lower atmosphere. You affect the albedo, the amount of sunlight that's reflected from the surface. And again, locally and probably regionally, you have the ability to influence the climate. So how do we put it all together? How do we, before putting it all together and trying to disentangle the various effects that I've showed you, another thing that we do is we change the surface of the land by urbanization. And this is just a little animation of the growth of Los Angeles from the 1800s through to the present. And you see in the 1920s, the rapid expansion of Los Angeles. Again, we're changing the surface of the planet, not only here, but at mega cities around the world. And that has some implications for local climate. So this is a figure from the 2017 National Climate Assessment, and it's an attempt to put it all together, to make sense of the information I gave you, to take what you see on the top panel, the estimate of global mean surface temperature change from roughly 1860 through to the present, and to partition that into a solar component. That's the red line. You nicely see that 11-year solar cycle that I mentioned earlier, but you see in that second panel that there's no strong overall increase in the solar component of global mean temperature change over the 20th century. In the third panel in blue, you see the cooling that we discussed associated with major volcanic eruptions. The biggest blue spike there towards the right of the record, that's the cooling caused by Pinatubo. The fourth panel from the top, the green line, that's natural internal climate variability. Those big warm and cool spikes are El Niños and La Niñas, but again, no overall increase in, in the green line over the 20th century. And if you look at the bottom panel, that's the human component. So greenhouse gas increases, particulate pollution changes. It's the sum total of all the human influences. And look at the scale of that is substantially larger if you look at the y-axis. The scale of the human component is much larger than the natural variability component, than the volcano component, and then the solar component. So the bottom line is this. This is a figure that looks at the last 60 years and tries to explain how much of the observed global warming, that's the bar at the top there, the black bar, is due to these different factors. And the bottom line is that it's human-caused increases in greenhouse gases that explain more, actually, than the observed warming. And if you look at the yellow bar, that's particulate pollution. So the observed warming caused by greenhouse gas increases has been slightly offset by the cooling that we've caused by sulfate pollution. And you can also see that the natural factors, the sun and volcanoes, have been a small player over the last 60 years, as has internal climate variability. Think things like El Niños and La Niñas. So this is our best understanding of the relative contributions of different factors to observe climate change. Final slide. I tried to show you that it's not an either-or proposition. All human effects on climate, all natural. Our climate at any one point in time is influenced by both natural and human factors. The natural factors include things like the sun's energy output and how it varies on timescales of 11 years and longer, and volcanic aerosol particles in the atmosphere. There's also this rich month to month, year to year, decade to decade natural climate variability that has nothing to do with the sun and volcanoes, phenomena like El Niños and La Niñas. But in addition to these natural factors, there are strong human effects on climate due to burning of fossil fuels and the increases in heat-trapping greenhouse gases that has caused, due to changes in particulate pollution, and due to modifications to the land surface arising from things like deforestation and urbanization. And as I showed you in the last slide, when you put it all together and try to separate these individual natural and human influences, our best understanding, not just from that figure, but from a variety of different sources, is that the climate signals the warming that we are causing by human activities is substantially larger than the noise due to natural events only. So thanks very much, and I'd be happy to answer any questions you might have.
Thank you so much, Ben. If you have any questions, please send them to the chat box and I will read them off to Dr. Santer. So we'll wait here for a moment to see if anyone. First question, and maybe you know some good sources. Can we get easily usable data sets like this to work with? Do you know of some good places to find them to access it for to work with teachers and students?
I'm sure that Frank, who's on the line, is a much better person to answer that question than I am. I would say that both NOAA and NASA have incredible resources in terms of data. So much of the temperature data that I showed you today is available at NOAA. All of the computer model data that I use is freely available. If you go to a website called CMIP, Coupled Model Intercomparison Program, then climate model simulation output is available there. But I'll let Frank reply. Maybe he planned to cover that in his remarks later.
Yeah, I'll let you pop in a second, Frank. Deb was she elaborated a little bit. She said it's hard to sift through the data if there's a key portal for key data, and maybe Frank, you know of some too. Otherwise, if
sure, can you hear me, Chris?
Yes.
Okay. So one of the challenges that we've been trying to wrestle both at NOAA and NASA and others in the climate community is being able to pull down the data. Sometimes is actually a really hard problem. And so one of the solutions we've been working with at NOAA in climate.gov and in specifically the US Climate Resilience Toolkit, a wonderful website that has some of this information, is to be able to provide people access to the data and the tools to do the analysis within the browser, as opposed to trying to pull it all down local, because there's so many versions of all of these key data sets. Knowing which one is the right one, you know, a lot of the analysis that Dr. Santer was showing, there are key data sets that have been, you know, gone through analysis and quality control to make sure this is the right version, and you want to be working off of that one. So, but you know, maybe Chris and I can provide some of those links of the best places I know to get that information in a subsequent email or document if you're sharing resources that way. And you're on mute.
I keep coughing, so I turn it off. The Resilience Toolkit and all those links will be in the follow-up email. So each of you on this webinar, and if you are listening to the recording, there's a document that'll have all those links. So yes, absolutely. Is there any other questions that people have? I think you just answered the question so well, Ben, that, all right, well if there's
my presentation is freely available too. It's all of the information I presented today is in the public domain. So I'm happy for you, Kristen, to share it with anyone who wants to delve deeper into the information I presented today. And in the case of almost all the slides, I think there are links to where the information was obtained from as well.
Great, many thanks. There is one last question. I think it would be something that people might want to hear the answer to, and that was, what are the major challenges that you face when you talk with people about this topic? What's your biggest one?
As I mentioned, I try to be accountable in the public arena. I'm funded by the Department of Energy. Almost all of my work has DOE funding. And in my opinion, I need to explain to people what I did with the funding, what I learned, and why it matters to them. And I take that responsibility very seriously. I give about 20 to 30 public presentations on all aspects of the science that we do, not just to my peers, but often to people who are skeptical about me and about everything that I do and everything that I presented here today. That's part of my job. And I would say that that's challenging, but it's also what we need. At a time of shrill political discourse, we need respectful dialogue about this issue, about what the basic facts of the matter are, what likely outcomes are for our climate system and for us if we incorrectly dismiss the problem as a hoax or a conspiracy. So these are challenging times. It's like the line in that Dickens novel, Tale of Two Cities. It was the best of times, it was the worst of times. Sometimes tough to talk about this kind of work in the public arena. But on the other hand, like it or not, climate science has been elevated in public discourse. And there are tremendous opportunities to have that respectful dialogue, to talk about the problem, to talk about the science, to talk about the evidence. And that's what I want. I want those opportunities like today's opportunity to interact with students, with politicians, with the media, and to convey the joy of scientific discovery. This is an incredible detective story, figuring out and teasing out human effects on climate from the natural effects on climate. So let's have those opportunities to explain that joy of figuring stuff out.
Thank you so much. And Deb was saying thank you so much too. We're going to move on because we want to share just a few curriculum resources that really, I think, are going to be great for helping bring your presentation into context. So feel free to stay on, or I'll shift it over to Jenna, who's going to be sharing the screen and moving on. So thank you. A round of applause, silent applause from us out here.
Great, thank you so much, Kristen. I am Jenna Totz, a Climate Change Education Manager at Climate Generation, and I just want to share a resource for you. That resource is Next Generation Climate. It is a resource for grades 6 through 12 that we wrote a few years ago, and it supports NGSS. A couple of key pieces in that curriculum are claims and evidence and reasoning that come up in 2 different lessons, as well as argumentation, and then a lot of time in reading graphs and looking at data. And as a former earth science teacher, I know that is something that students need some time, additional time working on. It's free to download, so you can use that URL there. Otherwise, I'm sure it'll be in the follow-up email. So these are the performance expectations that Next Gen Climate looks through. The key one today that we're looking at in the weather and climate area, but also looking at human impacts. And then lesson 6 goes into engineering design. So I want to focus just for a few minutes on what's happening to global temperature, which is the introduction activity of lesson 1. And a key piece that's important in this activity is the importance of asking clarifying questions and making sure that the data that you're looking at is reputable and comes from a good source. So looking at things like who collected the data, does it represent what it's supposed to, and who funded that research. Another activity that you could bring in from this one coming from the CLEAN network, which Frank will talk about here in a moment, is the stink test, where you're validating resources. And so looking at how to recognize if a source is valid or not. Looking at that source, is it timely? Is the information presented important? Is there any bias presented? And is that knowledge accurate? So again, that comes from CLEAN, and Frank will mention a little bit more about that. All right, so what I would love for you to do right now is to use your chat box to look at this graph that's presented here. Again, this is from the introduction lesson, and to just punch into the chat box what you notice about this 25-year segment. So we're just looking at a chunk of a graph, and just write in the chat box what you notice. And Kristen, if you want to read off some of those, I don't want to make my screen smaller because that graph is already pretty small. So if anybody writes in what they notice in the chat box about this particular graph.
Increasing trend, overall upward trend. Those are 2 comments. Thank you, Elizabeth and Janice. There is an increasing trend with some variation. That's another one.
All right, so we're going to move on. I have another graph chunk, but we'll just move on just to make sure that we've got enough time to finish up here. But this activity starts by handing out those graph segments to your students and asking them what they notice about the graph and what they see. And then once they have shared that information and digested some of that, to put them all together and to come up with this particular graph that looks at the change in temperature over time. And when you put that together, you see a much different picture than when you're looking at just the small segments. And it's really important, obviously, to look at all of that information as a whole and to look at change over time. And so these 2 graphs come from Skeptical Science, a reference that's been talked about already today, but a great resource. And the 2 graphs showing that if you are to cherry pick the data and only look at small sections, you could come to the conclusion that global warming or climate change is not happening. But when you put all of that information together, you in fact see that the trend is overwhelmingly increasing. The temperature is increasing. The rest of the lesson goes into the indicators of the rise in global temperature. So students are handed out pictures very similar to pictures that Ben Santer presented, and looking at some of those indicators of what is causing the rise in global temperature versus just looking at a temperature graph. So here looking at the, sorry, I've got information in the way here, damage caused by wildfires and Lyme's disease cases increasing. And then students use that information to answer some questions about the quality of the information and getting to understand what the data is showing. The key thing to remember here with lesson 1 is that the lessons become more in depth. Lesson 1 is really about establishing a foundation and figuring out how to read these graphs and data. And as the lessons become more in depth, that's when the students start participating in things like claims, evidence, and reasoning. The lessons are very adaptable to your area. One great resource to use would be the National Climate Assessment, which Ben mentioned, to find more place-based data. You could find specific data for the Northwest if you wanted to be a little bit more specific to where you are. So the rest of the Next Generation Climate, real quick, lesson 2 looks at the factors that have actually caused the rise in global temperature. The greenhouse effect game is a wonderful model that really shows how the greenhouse effect works. Lesson 3 looks at the repercussions of that rise in global temperature, again, using the National Climate Assessment to do some research, again, specific to your area. Lesson 4 looks at the ways to monitor those repercussions. So reading about what scientists are doing across the country, as well as becoming a citizen science, letting your students find data within their schoolyard and present on that. Lesson 5 looks at repercussions of the climate change. How can those repercussions be minimized? Learning things like adaptation and mitigation. And then 6 is my favorite. Your students are actually designing a method to monitor and minimize climate change. They're using engineering design principles in order to, say, monitor the waste in the cafeteria and then minimize that waste, hopefully through some form of composting that they would do. Lastly, just a couple of other resources from Climate Generation. Our Teach Climate Network is open to educators around the country. One, it's a Cli-Fi book club, so we read some amazing climate change fiction and nonfiction books and discuss, but then also talk about the challenges and successes that we're facing as climate change educators. We also provide other curricula besides the Next Generation Climate, so you can check that out, and provide professional development to teachers around the country. Our Summer Institute this year will actually be in Washington, D.C., but we'll also have some local workshops for Minnesota educators and hoping to take our show on the road more often.
Awesome. Thank you, Jenna. If you could go to the next slide for Frank. So I didn't introduce Frank, but Frank is with us from NOAA. Thank you, Frank, for joining us, and you can introduce yourself.
Fantastic. Thank you, Kristen and Jenna and Dr. Santer. This is, and also Ellen and your team, this is a wonderful opportunity for all of us to come together to support this really rich and important opportunity that's happening in Washington State. My name is Frank Niepold. I'm the Climate Education Coordinator at NOAA in the Climate Program Office, and I've been working here for about 14 years, really trying to figure out how to build climate and energy literacy across the nation. And one of the things in our last minutes here that I wanted to make sure we've learned is we've worked at climate and global change education for decades. It's been sometime in the 70s, sometimes in the 80s, sometimes in the 90s, and it's been coming and going and coming and going. But really where we are right now is this huge opportunity to do this much more at a system level. And in order to support thousands and thousands and thousands of teachers supporting millions and millions of students, we need a much more comprehensive approach. And that the only way we can do that is weaving together all these rich opportunities that the scientific community, the education community, and organizations like Kristen's have come together. And so what we tried to do last year was trying to weave it together in a much more cohesive, common, integrated approach. So the toolbox that I'm showing you here is that. And one of the key things I just want to highlight is this ACT, the dark green box there. Turns out that students really want to take their learning about this issue and translate it into individual and collective action. It's an important part of the learning cycle, so we created something called the Climate Learning Action Process. And that's a new thing. Any feedback on this, whether or not this relates to you and what you feel, that would be wonderful. I know our time is short, so I want to, if you can go to the next slide, Jenna. One of the groups that came together to support this is called the CLEAN Network, the Climate Literacy and Energy Awareness Network. That's the unpacked name. All of us are members of this in one way or another, and we continue to do this. But one of the most important things we've done over the CLEAN Network is the CLEAN collection. And so a couple of things on this. If the teachers in Washington State, those who are with us today or those who are watching, want to suggest excellent resources that you and your grantees or partners have come up with, please, by all means, let us know where they are. We always are adding more excellent resources. So that suggest is actually for anyone to suggest an excellent resource that should come in, because we're always finding more coherence. That's really what we're about. But the collection is this. What we tried to do is figure out how to make the internet useful for this purpose. Turns out there's a lot of really awesome educational materials on climate and energy that are hidden under a lot of really, really poor quality, poor science, old and broken things that you still find. And that's not something that's very friendly to teachers' time. And that's the most important resource you guys have. So to respect that, we've been curating this collection of these excellent resources. Check it out. And the last one, just again, and it's a consortium of partners have been making that happen. But the last one is some work we did over the last couple of years to align all these disparate, disconnected resources with these new standards. And the tool that I'm showing you here gives you an ability to search by the exact standard you're talking about here in this talk, or any other one that's in middle and high school, and find out what do we see that's out there in digital free space that is related to what you're trying to focus on. And share this with your colleagues, find out if it helps you in what you're trying to do with building your resources, your units, your lessons. I think you're gonna find this is a very valuable place to go to start to look for new resources. It's not the only place, but it's a great place to start. And it gives you a lot of information about those resources beyond the developer's intent that I think is important. But the last piece of this is really important, is that people like Dr. Santer or others review these resources on top of the education review. And we only put in things that pass the scientific test. And some things used to be good, but they're not good anymore. Or sometimes they were never scientifically sound, but you can find your way to them, and we point to not those. So I really appreciate this opportunity to work with you guys, and I know we're out of time, so I'll leave it there.
Thank you. And just an add-on to that too, make sure you sign up for our next webinar. It's kind of a good segue, because we will be featuring one of the newest parts of the CLEAN collection, which are some of the units that have been pulled together. One of the CLEAN's friends, Cheryl Manning, will be joining us to highlight that. So make sure you sign up for our next webinar, February 25th. And thank you again for joining us today. There will be a survey that pops up when the webinar ends, so please wait for that to pop up. It will be coming in the follow-up email as well. I'll be emailing all of you this week the resources that were mentioned and a link to the fully recorded webinar. If you have any follow-up questions or comments, please feel free to contact me. I can connect you to the folks that were on the webinar. And thank you once again so much, Dr. Santer and Frank and Jenna, for joining us today, and to the state of Washington for making this possible. Have a great day, and hopefully we'll see you in a couple of weeks for our last webinar.
Thank you, Kristen.
Thanks, everyone.